Hello and welcome to part 12 of Dev Maths and Stats Refresher Course, Lecture 5, where we're looking at optimization, this time with inequality constraints. So with inequality constraints, we face the problem that the optimal solution might not actually be on the constraint curve. So we look back at the second of today's examples. We saw that when we changed from 2x plus y is 8 to 2x plus y can be 9, that means you can get a little bit more for maximum value, approximately given by lambda. So what happens if something was written like this? Instead of 2x plus y equals 8, it's less than or equal to 8. That's an inequality constraint. That means you can choose x or y on the line or from anywhere beneath that line. So if we nip back and try and find where that is, that actual graph, which I think is in here. So in this case, if we get the x and the y axis the right way around, we can choose any way you want. Here's x and y. So you can go any way you want. So 2x plus y can be anywhere up to 8 here, which means you could, if you wanted, to have some place below that. But in fact, in that case, if you could choose anywhere below this or up to the line, this is still the best place to go up to here. So that wouldn't actually change the answer in that case. You would want to have the maximum. And in fact, even if you went to 9, you would still want to stick with that. So if you're allowed to have up to 9, then you would go right up to the line and choose this point here. So in both those cases, what we say, we still choose the point right on the line. We say the constraint is binding, so it is satisfied with equality. So even though you're allowed to have less than or equals 8 or less than or equals 9, the best point is to go right up to that, onto the constraint line, so the constraint is binding. If you could, you'd want to have more, but you can't, so you're right up against the constraint. However, what happens if you relax the constraint still further? So let's just define it all again. But this time, can't even remember, I've relaxed it to all the way to 20. So here you've got the situation where this one, the first problem, you're allowed to have up to 8. Now we can have up to 20. So it's 2x plus y is less than or equal to 20. Now, in this second case, you can see that the optimum solution would not be here, because now we have gone past the peak. So in this case, the optimum solution would be to stay here, and we wouldn't care about the constraint. So we could say the constraint would not be binding. And in the horrible language that someone made up for this, that means the constraint is slack at this point. Slack or non-binding. So what this means is really that even though what comes looks a bit complicated, it's just a fancy way of saying that it adjusts the conditions to say that either we're in the case where the constraint is binding, so we need those Lagrangian conditions to be satisfied, or we can forget some of those and we just go back to the unconstrained optimization and just satisfy the usual first order conditions to get here. So it's just making us systematically check through, comparing this point with this point here and seeing which one's working better effectively. So the way it's set out is this. If you want to maximize this subject to this condition, then you make the Lagrangian in the same way. And this time, this time the first order conditions are known as the Kuhn-Tucker condition. And really this is one of the reasons I like to teach this, is because there just as many articles like to say, oh, we assume a monotonic increasing function and this function is quasi-convex. Oftentimes you just meet this, we're going to use the Kuhn-Tucker conditions, and the first order, the Kuhn-Tucker conditions give this condition. So the Kuhn-Tucker conditions just mean the formulation of these maximization or minimization problems subject to an inequality constraint. So as before, you make the Lagrangian exactly the same. And as before, this and this must be equal to 0. But for lambda, it's got to be the differential, the derivative of L with respect to lambda has got to be greater than or equal to 0. And also, as well as this, you have these two extra conditions that either lambda times the derivative of L with respect to lambda has got to be equal to 0. And this part here essentially means that either this is 0 or this is 0. So either lambda itself is 0 or the derivative is 0. And the last condition is known as complementary slackness condition, which is a very ugly expression. So this part here is just equal to the constraint. So when the constraint is binding at a solution, if the constraint is binding, that means this is 0, so that part's 0. That means that this doesn't have to be 0. Yeah. So if the constraint is binding, this doesn't have to be 0, and this represents the value of relaxity constraint. If the constraint isn't binding, then lambda is 0, which essentially means that you don't care about relaxity constraint. You don't often see them written in this form. Then the Kuhn-Tucker conditions are more often written in this form, which is when you also add in that x and y can't be 0, can't be less than 0, because very, very many, often you're dealing with like, how many people should be allocated to this, how much money should be allocated to this, what's the crop yield or whatever, and all these things are positive. So you don't want to come up with some solution that says have negative answers. So the full set of Kuhn-Tucker conditions with the non-negativity constraints look like this to maximise for a maximisation problem, which is that the Lagrangian derivative's got to be less than 0, x has got to be greater than 0, and one of those things has got to be actually equal to 0. Same for y. The derivative's got to be less than 0, y's got to be greater than 0, and y times the Lagrangian's got to be equal to 0, and the same thing for lambda. That only applies to maximisation problems. There's an equivalent set for minimisation problems with the direction of some of the inequalities reversed, like this. Okay, and once you've seen a few examples, it becomes easier to understand why these are written out like this. But I'm not going to be testing on exactly why all these things are written out in the order they are, or how to solve them in great detail in the exam, though we might look at some examples of those on the problem sheets. Okay, that brings us to the end of this section, so look forward to seeing how we go on with the problems, but for now, thanks for watching.